Now, this carbon has 3 hydrogens. If this bond is broken down or cleaved homolytically, what does that mean? The bond breaks homolytically. Now break those 2 words. There is a homo and a lytic. What do you think that means? What does homo mean? Same. And lytic, what is the root word for lytic? Lysis. What does lysis mean? Breaking. So, if lysis means breaking, what does photolysis means? Break the word. Photo and lysis. What is the root word for photo? Where is it coming from? Photon. What does that mean? Light. So a thing that is breaking because of light, that is photolysis. Here I am saying breaking the bond homolytically. What can that mean? So this bond has 2 electrons and I am saying homolytic cleavage, homolytic fission. What will that mean? Breaks, and each of them just take their 2 electrons and go away. So carbon once gets 1 electron, hydrogen gets 1 electron, and they move away. No one gets a charge because they just got the electron that they had in the beginning. So no one gets a charge. What do you generate? What is that thing called? So if you have a carbon and a hydrogen, and this bond has 2 electrons, right? This one of them gets 1 of the electrons, the other gets the other. What do you generate? A C dot and an H dot. What do you call these things? They are called free radicals. This is the free radical that we talk about. When you have free radicals in your body and everything. This is the free radical. This happens a lot when you have UV interference. So if there is UV shining on anything, you will generally get a lot of these free radicals. This is a free radical. So when do you get a free radical? When this bond is cleaved homolytically, homolysis. You get free radicals. These are free radicals. Now, you can break this bond heterolytically, in which both these electrons will now go to one of them. If it has to break and go to one of them, who will take that? Carbon or hydrogen? Who has the more tendency to take it? Carbon, because it is more electronegative than hydrogen. What will this produce? A heterolytic fission or cleavage of the bond is going to produce charged ions. So it will produce an anion and a cation. What is the charge on carbon? Because of this minus, just a minus, no -2. Because 1 electron was already its own. You see, when it got 1, I didn't say it got a minus charge. There is no charge here. This is where you get the charge. So when a bond breaks and both the electrons are taken up by the one of them, that thing will get a negative charge, not -2, just -1. Because one of the bonds was one of the electrons, it was its own electron, but it got the additional electron. That's why we have got a -1. There is no -2. Clear? So this is the anion, this is the cation. There has to be charge balance in everything. You cannot have charge floating around, right? So tell me, what is the charge on this carbon when this bond broke? What is the charge on this carbon? -1. Now we'll have to compare the stability of this compound to the stability of this compound. Tell me which is more stable. You can look into these two and see that there are negative charges on both of them. See, I might like to eat a lot of food, but if I cannot digest that food, I will not be stable after eating that food. So, carbon ate a lot of food in this case. In food in here means the electron. In that case, oxygen ate a lot of food. But who do you think can eat that and still be fine? What is that property that will help you to decide? So you eat electrons and still be fine with it. Which is that property? Electronegativity, not affinity. It's the electronegativity. So, tell me which is more stable, O minus or C minus? Why?
It's more electronegative.
Is carbon more electronegative than oxygen? Amber? It is, can you tell me the position? Which is more electronegative? Agreed? So which will be more stable, this or that? This one will be more stable. So my question is this hydrogen more acidic or this hydrogen more acidic? A or B, which is more acidic? Because I converted the question of which is more acidic into the stability of the products. So the product which is more stable, so this is more stable, this will produce more of HAs. If I am stable after leaving hydrogen, it's fine, I'm more stable. But carbon is not that stable. So will carbon leave hydrogen? It will say no. Dude, please don't leave. Because if you leave, I will become unstable. So I won't let that hydrogen leave. Oxygen will just kick it out. Hey, just get lost. It's an electron snatcher. It's more electronegative. So it is fine with this. And that is why this hydrogen is acidic and that hydrogen is not. So I also give you a definition of acidic H, which was what? The hydrogens that are attached to an electronegative atom. That hydrogen is an acidic H. What are the electronegative atoms? Oxygen, chlorine, fluorine, maybe nitrogen, right? So all these really electronegative atoms, when they are attached, when a hydrogen attached to them, then that hydrogen can actually leave, because that bond will, the electrons in the bond will be taken up by the more electronegative atom, correct? Is this absolutely clear? Right? So the concept of acidic H is what? Those hydrogens that are bonded to more electronegative atoms, like things like these. So those will become acidic H. Correct? Okay. With this idea, tell me which of these three will act as an acid or can act as an acid? So it is the same thing. So you remove an hydrogen and produce and see the species in all these three, and then tell me which is the most stable. The one which produces the most stable species out of these three will be the most acidic. That's what we did with that acetic acid, right? So what is the species that you will produce if you remove an H plus from here? So maybe I just remove one of the hydrogens in here. So what is the charge? And then you get the H plus. For this, agreed? For this, right? Which of these three are the most stable? Think about this. Why?
Because the SP is a bigger.
Correct. So this is sp3, or this carbon was sp3, right? This carbon was what? sp2. What was this carbon? sp. I have written the electronegativity here. So this is the most electronegative. This has the negative charge. So this becomes the most stable. So this is the most stable. If this is the most stable, then the likelihood of this H leaving becomes more likely. And you can see this in the lab as well. So this is an alkane, as we call it. And we'll look into that. This does not react with bases. Neither the others. So even CH2 does not react with the bases. CH does not react with the bases. But acetic acid, whose name is an acid, right? CH3COOH, reacts with the base. So it can react with NaOH. Okay? These will not. But there are certain other things other than bases that can interact with that H thing. For example, sodium metal. So sodium metal becomes really reactive, right? So sodium metal is very reactive. So if you give sodium metal to this thing, nothing happens. Even this, nothing happens. But give sodium metal to C2H2, it is going to react with that because of this H, which is slightly more acidic than these. But is this H super acidic like the acetic acid H? No, it's not. But relatively, it is more acidic. Make sense? So this is also going to play an important part. The H, from where these H's, because a lot of these organic compounds are what? CNH, like CNH, that's what it is. And you get water. Now water has all this seat of acidic behavior, whatever comes from water. So water, when you split, becomes H plus and OH minus. And what is an acid? That gives H plus. What is a base? That gives OH minus. So water can act both as an acid and a base, given the situation. If someone is more acidic than water and comes and reacts with water, water will behave as a base. But if someone is less acidic than water, water will behave as an acid. So water has both these properties. So this relationship with H and OH, it's deeply, and you're learning this in aqueous geochem. Water, pH 7. Where do you get that pH 7? It's the water. The pKa of water is 14. I'm not getting into that in here, okay? But this H plus OH minus business is very important. Anywhere you have water, anywhere where you have these organics, this becomes important, okay? Now, with this knowledge, let's look into some of the functional groups or types of organic molecules that we generally have. Now, the functional group you can imagine as you have a carbon chain, okay? So say you have a carbon chain. And then you have something attached somewhere. I'm calling it the functional group. This small addition will change the entire property of the compound. Or that small thing will be the seat of reactivity for that entire compound. That's why we call it the functional group. So this functional group, although it might look very small as compared to the big carbon chain, but the seat of reactivity is that functional group. Either things will start reacting from that, or that is going to react with something else, either of these two. So that is the functional group. Also, not just the chemical reactivity, the physical behaviors like boiling point, melting point, all those kinds of things will also be determined by what type of functional group that you have. Okay? The simplest type of organic molecules will be what? In which you have no functional groups. Correct? This is the simplest type of organic compounds. Right? So you only have carbons, and so each carbon is going to have 4 valencies, right? And now know that all these are sp3 hybridized carbon, and all these carbons have a tetrahedral geometry around its molecule. I'm not representing it in here. Very simplistically, I'm just drawing it out in squares. How do you satisfy the valencies of these carbons? What comes in? What is the most abundant thing in the universe? Hydrogen. So you get a carbon and a hydrogen at all these positions. What will you call this thing? Call this hydrocarbon. Because that's what this is. It is just a carbon chain, and all the valencies of carbon that are remaining are being satisfied by the hydrogens. So it's called a hydrocarbon. This is also the simplest hydrocarbon, simplest class of hydrocarbons, because what is the type of bond that you have in here? What are the types of bonds? All single, all sigma. So this type of hydrocarbon in which all bonds are single is called, it's an alkane. Right? Now, depending upon the number of carbon atoms, we also give names to these different compounds. Okay? What we will do is, we'll just write a few of them in here. So when the number of carbon is 1, you get a prefix of correct? So anytime you see the word meth anywhere, that is signifying that there is something related to one carbon. Eth 2, prop 3, bute, no, it's not butane, it's butane, right? Pentane, hexane, heptane, octane, nonane, decane. When it becomes 11, undecane, dodecane, tridecane, tetradecane, pentadecane, things like that, right? So, in this alkane, this is where you will get the name. So this is the prefix, that is the postfix. Like that, this is where you start, that is where you end. So if you have one carbon only, and all these are satisfied with hydrogen, what is the formula? CH4, correct? For 2 C's, what will be the formula? So give me a general formula. So what is the first? Methane. What is the formula for methane? CH4, right? So put N is equal to 1, you get CH4. The name becomes methane. Put N is equal to 2, becomes C2H6. Name becomes ethane. C3, tell me the formula. C3, what will be the hydrogen? 8. What will be the name? Propane. And you can just go on, right? As simple as that. Any confusion? Now you can have different chains and stuff like that, right? So what is the name of this compound? 1, 2, 3, 4, 5, 6. Without counting the hydrogens, tell me the formula. Don't count from the formula. 14. It will match. Right? Now, I can change the chain, right? But the formula will remain the same. It will become C6H14. The formula will remain the same. But the names will change because, of course, like that's a different structure. This is a different structure. So when two things have same molecular formula, but different molecular structure, what is that relationship called? Isomerism. So these two are isomers of each other. I will not get into the isomers, okay? But this is alkane. Now, similar to it, you have, I have given you a list in which you have all these different functional groups. So let's get over a few of the functional groups. So you had alkenes, right? What is the next thing on your list? Alkene. What do you think is the special thing about that functional group? What is happening?
The bonds between the carbons.
Is what?
There's a bond.
There is a pi bond. So in an alkane, there were no pi bonds in alkane. But in alkene, there will be at least one double bond. At least one double bond. If it has one double bond, then the formula will become very simple. CnH2n. For example, C2H4. What is the name of this thing? If there is an alkene with this, look here, look into the prefix here and the postfix there. Amber. Ethene. And how will it look? Right? And then you can have, what is the name of this? How many carbons? 5. So what will be the base word? Pent. And what will be the last word? So pentene. Also we can call this 1 pentene because the double bond is in first carbon. If I shift this into this, this becomes 2 pentene or pent-2ene. Okay, very simplistically. So I'm not getting into the nomenclatures and things like that. But this is what it is. I mean, it's a way to represent these organic molecules, right? Are we still in the hydrocarbons? Yes, because we are still in making things from hydrogen and carbon, hydrocarbons, correct? Now, this is called a saturated hydrocarbon, the alkane, because all the bonds are single bonds. A single bond is better because you get head-on overlaps. That is saturated. So what will you call alkene? Unsaturated. Which will be more reactive? The unsaturated ones, because it is actually unsaturated. Because that will want to react with what? Can you give me an example? What will this 2-pentene want to react with and become something else? What will that be? So if I'm pentene, I have a double bond. What do I want to do? Am I happy with that double bond? I want to remove that double bond somehow. Because after all, that is making me unsaturated, unfulfilled. What will it try to do?
It will try to make single bond.
How will it do that?
Addition of hydrogen.
That's what it will do. So it will react with a hydrogen and get those 2 hydrogens and become pentane. This kind of reaction is called, give a name to this. Give a name to this reaction in which an unsaturated compound is reacting with hydrogen. There is no lysis, right? There is no hydrolysis. Hydration is, okay, what is hydration? So when I drink water, I become hydrated. So what is addition of water is called hydration. This is not addition of water. What is removal of water? Dehydration. And we'll see dehydration reactions happening a lot. But this is hydrogenation. Addition of hydrogen. So hydrogenation. Addition of water is hydration. Now tell me if you have a compound which is this. What is the name of this compound? Look into your sheets. What is the name of this thing? What is the formula of this thing? What is the name of this thing? You know everything. You know the reactivity. Whether this will be more reactive than alkene? Whether alkyne will be more reactive than alkene? Yes or no? Is this unsaturated or saturated? I am carbon. I am fully fine when I have 4 sigma bonds. Currently, on that one carbon, I have 1 sigma. There is another sigma here, but there are 2 pi's. Am I happy with those 2 pi's? Does it mean? No. I have 2 pi bonds as compared to the 1 pi bond in alkene. So am I more reactive than alkene or less reactive? More reactive. Because I'm not satisfied. So if I'm satisfied, I won't react. If I'm not satisfied, I will react. So an alkyne will be more reactive than alkene. And what is the name of this thing? Give me the name. Come on, you know all this. Give me the name. What is the root word? How would you find that root word? How many carbons? 4. What will be the root word? Bute. What will be the final word?